Hi everyone. My name is Dr. Matthew Michael. I'm from NJIT. I'm going to be continuing on my videos talking about series of ordinary points. So we're talking about differential equations and talking about how we can use series in such a way that can solve a differential equation. Rather than exponentials, polynomials, trigonometric functions, we can also use those ugly things from Calc 2 in a useful manner. We'll be talking about that. I'm also going to be catching up and doing a bunch of these videos in one day. So hopefully that'll help. So, in Chapter 3 we talked about the different things in second order with constant coefficients. Well, this time we're not going to have constant coefficients anymore because most differential equations don't. Especially in a real-world scenario, we're going to need to have more complicated setup. So with this in mind, we need to be able to solve these. And oftentimes series might be the best or maybe only solution to solve these in the typical sense. So we're going to be using series. And so the solution that we're going to be focusing on most is the homogeneous equation. Big P of x, y double prime, plus big Q of x, y prime, plus r of x, y is equal to 0. And I'll be talking about why it's good enough to just use the homogeneous case a little bit later, because non-homogeneous won't make much all a difference when we solve this. It'll just have an effect on our recurrence relation. When we deal with the cases, on all of our cases, our P, Q, and R are going to be polynomials. But the most important part of the theory is that they're continuous. But in almost all your cases, you're going to be seeing polynomials because they're a lot simpler to work with. But these also definitely work for pretty much any continuous function. So you might occasionally see one of these where P, Q, or R is like sine or cosine. Because remember, we have those Maclaurin series and other Taylor series of those functions. If you ever see the word analytic, analytic is a very special term, used a lot of complex variables. For now and in this class, we're going to assume that analytic means continuous. There are more complicated things involved, but analytic in our case would mean continuous. So, P, Q, and R, polynomials with no common factors. We're going to be looking for solutions around some point of interest, x naught. Now, when we plug in that x naught into our front of our equation, P of x, out in the very, very front, it is not equal to 0, we say that it is ordinary. Nothing special happens, nothing causes anything to blow up. So, okay, we like that. We call it a continuous point. And so we're going to be around those ordinary points today is how big of a solution we can find around those points. As long as we avoid those places where P of x is equal to 0. And this is why it's important that P of x is not equal to 0. Not only do we lose information, i.e. we lose a second order differential equation here, there's no y double prime anymore, it just becomes a single or a first order setup. When we divide out, because it's nice and easy to think about it in this sense, little p and little q of x, notice this p of x on the bottom, if it's equal to 0, we have an undefined ratio here, undefined rational function. But if p and q are continuous, we can call way back into Chapter 3 when we were talking about the original theory with Wronskians and the like. So according to Theorem 3.2.1 from Section 3.2, we know that there's a unique solution if we have initial conditions for the first derivative and the function itself, initial velocity and initial position. Now, just like we have a special name for when P of x does not equal to 0, we also have a special name for when it's equal to 0. It's called the singular points. I like calling them singularities because it reminds me of the ideas of black holes, because singularities in black holes are sometimes described as a loss of information. So if we have a singularity out front, at the singularity we lose information. We lose the second order derivative as we move towards that x naught. And those little p and q's of x go nuts. So, we're going to be talking about those in sections 5.4 and 5.5. So those are another two videos I'm going to be doing tonight. So, we need to solve our equation near some ordinary point. Not singular, so p of x, a-okay. Well, remember we just talked about reviewed power series. Well, we can plug in a general power series with coefficient an into our differential equation. We might be able to find some coefficients that have some discernible pattern in such a way that we can solve this differential equation, as long as it's near an ordinary point. Something special happens near those singular points. Now, it's easy enough to take derivatives. We did this in Calc 1. We can make the derivative operator move inside of a sum, and since the sigma is just an infinite number of things added together, just move the derivative inside, and it's just a simple power rule. Move the n out front, and exponent is now n minus 1. So, easy peasy. Let's do one of the easiest differential equations. Maybe not easiest, but second order. But it's pretty easy. Y double prime plus y is equal to 0. Remember, back to this has constant coefficients. We can use series, but if we were to use constants, we'd see that r squared plus 1 is equal to 0. That's cosine and sine. So chances are our solutions will be our Maclaurin series if we center around 0, which we will to make life easier, because really, do you want to have something else hanging out inside that n? So, let x not equal to 0 for simplicity. We're going to be, my best guess is that our solutions will be the Maclaurin series for sine and cosine. So let's check. Plug in for y, take the derivative, take the second derivative. Note that when I take the derivatives, some of the terms might disappear. For example, when I take the first derivative, and if I plugged in my first case n is equal to 0, my first term of the sum doesn't matter anymore, or because it's equal to 0. So I end up dropping that term because it's inconsequential. The same thing happens when I take the second derivative. Now the first two terms are inconsequential, which makes sense, because if I went back to the very beginning, a0 x to 0, that's just a0, because x to the 0 is just a constant 1. So what's the derivative of a constant? That's why it makes sense. So a1, x to the 1, take two derivatives. Any linear function, when you take two derivatives, goes bye-bye. So plug your derivative, second derivative, into y double prime, and plug your y into y. Well, simple index changes among friends aside, we can get a sum plus another sum. Now, we like this because we have an x to the n minus 2 and x to the n before, and now we just have x to the n's. So make your index changes always, so I go from x to the n minus 2 to x to the n. It's much simpler that way. We also lucked out because notice n is equal to 0, n is equal to 0. This is good because that means we can combine the sums to a single relation here. N plus 2, n plus 1, times n plus 1, a sub n plus 2. Remember, you need to do that sub-index change too. X to the n plus a to the n, x to the n. Combine them like terms, and we have this thing in brackets. Now, it'd be really, really boring if we just plugged in x is equal to 0, because then everything goes to 0. So, the only thing that becomes really important then is when x does not equal to 0. And so we have this thing. And if you remember back to the method undetermined coefficients way back in the day, we remember that when I had a polynomial as my forcing function on the right-hand side, okay, for you guys, right-hand side would be over here, okay, on the right-hand side, we plug in that polynomial, that type, into my original differential equation. And then we set these coefficients to these coefficients. We need to do the same thing here. I have a polynomial on my left-hand side, and I have a 0 polynomial, boring polynomials, but a polynomial on my right-hand side. Therefore, set these coefficients to these coefficients, these coefficients to these coefficients, which means since it's the same thing for all values of n, well, it's just a simple, what we call a recurrence relation. Solve for a n plus 2. Now, what happens if I don't have a homogeneous problem? Remember way back? It's just the method of determined coefficients. Maybe the first couple of values of n will be different. So, for example, if I plug in n is equal to 0 and 1, I might have actual coefficients that I'll need to solve with, not just equal to 0. In those cases, just plug it in. If not, then make sure to just plug in 0 if there aren't any things on the right-hand side. So, plug in a 2 on the left-hand side, because remember we solved for a n plus 0. Plug in n is equal to 0 for my first term, and I see that a2 is equal to negative a0 over 2 times 1. Now, what did I noticed that that plus 2 term is there, so that means that I can figure out an easy way to find the even numbers. So, I plug in the even numbers, and I start noticing a pattern, because I want to get it into its most simplistic form. And I start noticing oscillating or alternating series, and I notice on the bottom I have factorials. More specifically, the factorial is even. So, I notice this pattern. Patterns being key. So a sub 2 means there's a 2 factorial on the bottom. K is equal to 2. That would be a sub 4, which would mean it's 4 factorial on the bottom. Oh, look, there it is. A sub 6 means 6 factorial on the bottom, or k is equal to 3. Notice the k values being just 1, 2, 3, 4, 5. It does fit well with our nice alternating -1. So, we did it for the evens, let's do it for the odds. Oh look, it's the same one. Just slightly different when it comes here. So, I break my sum apart into even and odd sum, plug my terms in, zippity-doo-dah, I have Maclaurin series for cosine and sine. Cosine on the top, sine on the bottom. And notice that when I factor out an a0 and an a1 out of these two terms, because they're constants, I get the same sort of form that I did before. I still have a constant times a function. In this case, my function is cosine. In this case, it's sine. But still, a0 and a1 will be determined by initial conditions. Also, maybe due to forcing terms on the right-hand side. Keep that in mind. In that case, I'll be back later for more, and I hope that these are helpful.